pillow lava units that have formed in the hyaloclastite base of the island. Okay, again, the red color here is intended to represent the indurated material. We have free outflow of fresh water here only in the shallow region. But as we go deeper, the island actually acts like an inverted bowl. And given the hydrostatic head that we see within the saddle region, we could easily displace seawater all the way down to the old ocean floor. So these islands may have far more water contained, fresh water contained within them than we've ever given them credit for. And that's all I was going to say. So I'll be happy to answer questions. Yes.
John, do you have any idea, or does anybody have any idea what the source of the high horizontal compressive stresses might be that's even this thing?
Well, if this area has been intensively intruded by dikes, I would think that that could very well cause those very high horizontal stresses within the region. That at least makes sense to me, but you can probably answer that question better than I can. But does that sound like a reasonable hypothesis? No.
There are some others, but that would be at the top of my list.
Yeah. Okay.
Some questions and comments. Questions. Have you done any across that long MT line? Have you done any profiles in the other direction to give you a cross profile sort of sense of?
That's what we're doing right now. We just received permission from the Humu'ula command to go out and run two parallel north-south oriented lines perpendicular to that long cross saddle line, and we're actually going to form kind of a square where we've got the original line. We'll do the two cross profiles and a second east-west profile along the Mauna Loa flank, and really try to at least give us a minimum width of how far that extends.
Were you able to do any logging in the hole?
We have not been able to do any logging. The hole was so unstable in the shallow formation that it took us actually 2 or 3 tries to get the casing in the hole. We have still, the bottom of the hole is still open, but we're going to need to bring in some logging tools. I've since discovered how expensive logging tools are, $100,000 and up, to run them on a slick line in the hole. I'm going to try to do that, but we have not yet.
And sorry, so where you're proposing the next site, that seems to be west of the gravity high?
Well, I'm trying to shoot for the western edge of that gravity high. And again, based on what we're seeing with the resistivity profiles, I've tried to hit that. Because west of that, and this went before we really kind of had the information to make an interpretation. It was a point of curiosity that the high elevation, low resistivity formation seemed to run more or less horizontally. It didn't drop at the same rate as the surface contour did until it got over into that section where we're placing that second hole, and then it seems to drop more rapidly than the surface contour.
Can you show that picture?
Sure.
And can you sort of put your drilling result,
Hang on here.
resistivity?
Yeah.
So where you actually drilled?
Okay, we drilled.
Where are the water lenses on that figure?
It appears that our water begins right here and continuous all the way down.
Sorry, 700 to 1,200 feet and then
I don't know that we actually can see that shallower horizon. This is one of the drawbacks of the MT data, is that it doesn't do really well in the first kilometer of hole, or of depth. What we would need to do in order to see that is probably use audio magnetotellurics. And that's something we're actually hoping to secure an AMT system here in the near future to be able to resolve that shallower freshwater layer. But in the shallow zone, the MT is very long wavelength, and we just can't get good resolution in the shallow subsurface. But I'm sort of calling sort of this conductive zone here, and you see a very sort of steep drop off here in this 600 ohm-meter horizon. And that's kind of what I'm calling sort of the top of the water table here. Again, geophysics always tells you maybe. Yes?
Are you thinking at all about doing any crosshole geophysics? That's a pretty wide spacing for crossholes.
We've talked about actually using our casing in the central hole as an electrode, and sort of stepping off from that to see what we can learn, from that kind of a resistivity survey. It's something we'd like to do. The kind of the downside, though, here is that this borehole is located sort of around a lot of cultural noise. We're located essentially in the cantonment of PTA, and so they've got buried pipelines, they've got power lines, they've got sort of all kinds of stuff in there. So I don't know how definitive we can be. In the other hole, we might do better because it's much more isolated. We have much less cultural noise, and that might be a better prospect for doing that.
You mentioned, electromagnetic things.
Yeah, yeah.
Have you thought about maybe trying seismic?
I haven't, honestly. And I suspect it could be done. I think to a degree, I also have to recognize who's funding this. They're interested in the water. And I'm not sure, sort of, I've kind of pushed the Army as far as I think I can to do actual science. They've coughed up $6 million for this project, so I'm happy to work with them on this. Mike.
Don, I was wondering about your elevation for the source of the water, and that point seems to be an average of the elevation from where you drilled and the summit of the volcano. So I wondered if you're actually seeing water being sampled from the entire area.
Oh yeah, undoubtedly we are. Undoubtedly we are. But most of the water that falls above about 7,000 feet, and especially sort of on the leeward side of Mauna Kea, is derived from Kona storms. And typically those storms put the moisture fairly high up on the mountain. They're the ones that are responsible for the snowfall up at high elevation. But it is an average. It's really a combined average of all of the water that's fallen up that slope above where we're located. Yeah.
Any particular reason why you're favoring Mauna Kea as opposed to Mauna Loa as the recharge?
Well, I think there's really only where we're drilling, we're not even on Mauna Loa. Mauna Loa is going to be a relatively thin carapace of lavas over Mauna Kea for quite some distance to the south of us. Certainly it's possible that rainfall on Mauna Loa would be infiltrating, but what I'd have to do is think about sort of how the slope of Mauna Kea falls below that Mauna Loa carapace. And if similar to what we see with the interface of the of the two volcanoes in Hilo, above sea level, that interface was very soil and ash rich in Hilo. I expect it to be the same, so any rainfall on the Mauna Loa slopes would tend to be routed towards the south, down slope, down the old Mauna Kea slope, rather than to the north, which would really be up gradient. But again, with if those dikes actually are intruding into Mauna Kea, then possibly they could be confined there. So that's certainly a possibility as well. Yes.
On that same line, you don't think that there may be some intercalation of Mauna Loa and Mauna Kea strata?
Not in this area. We talked at length about looking for interfingering of lavas in the HSDP hole and the Hilo borehole, and we saw none of that. We were in Mauna Loa and then in Mauna Kea, and we saw no sign of Mauna Loa lavas once we got into Mauna Kea. If there is interfingering, I would expect it to be far to the south of us. Because, again, Mauna Kea concluded its shield building stage how many years ago, Mike? You know better than me.
Mauna Kea shield stage, probably at least 250,000 years.
Right. So figure that Mauna Loa was growing vigorously in that time period, and Mauna Kea probably very, very slowly. So the opportunity for interfingering is, I would expect to be pretty small.
Are you planning to do petrology? Anybody doing petrology?
We have a sort of some of the group of the Hawaii Scientific Drilling Project that will be looking at the rocks and doing geochemistry and petrology. But again, the reason that we collected them was to make them available to the community for that work. The most expensive thing about doing petrology, deep petrology, is getting the sample. So I've sort of gotten the sample, so everything else after that is cheap. So, Garrett.
So in our previous conversation, you mentioned water was getting hot. So
Yeah.
that implies a source of heat. Is that,
The dike system could potentially be a source of heat.
yeah, so is that coming from Mauna Loa then?
Well,
Or is it remnant heat from?
we don't know yet, and that's something that we are continuing to try to sort out. So, we're a long ways from an answer on that, but we're real interested in that answer. Mike?
Mauna Kea last erupted in this area 4,000 years
Right,
ago.
right.
So
Yeah.
it's certainly possible, and it was quite a sizable eruption from a number of different vents.
Mhm.
But having said that, there's also radial dikes coming down from Mauna Loa into this region that are 100, 150 years old.
Yeah. Yeah. So there you are. I mean, it could be from Mauna Loa.
I'm just wondering if you thought to look at the magnetic nature at all. If there is hydrothermal circulation, at least you're aware of Mauna Loa, that appears to break down the magnetite and the lava and give you a pronounced magnetic low over the hydrothermal circulation.
I have not. Are you thinking the Aeromag, island-wide Aeromag surveys? I haven't done that yet. That's something that we should definitely do and see if we can see that signature. Certainly we could take a look at those rocks to see sort of what the residual intensity is in there. Now, of course, we're not oriented north-south, so we can't do much more than that. Yes?
Yeah, what percentage core recovery do you get? Beautiful looking core boxes, but
I believe we are probably in the high 90%, mid to high 90%. It was, on the one hand, one of our drillers, who was no spring chicken, said this was absolutely the worst rock he'd ever drilled. But our drilling supervisor said that it was sort of a continuing surprise to him how well the recovery was going. When we get the core out of the core tube, it would just absolutely fall apart. but we did not have any severe problems while we were drilling of losing core or dropping core as we were recovering the core tube. So
Sloughing in.
we did have sloughing going on and rubble falling in, but we didn't lose much core. I mean, sometimes we would drill 10 feet and end up with 12, and we knew that 2 feet of that was garbage. But for the most part, I mean, we did have a few sections where we lost core in the very shallow zone. At one time, I mean, it was a driller's worst nightmare. I watched the driller as he drilled. We were actually trying to get back to recover the lost bottom hole assembly that we had gotten stuck in the hole. And I watched him with a rotary bit drill down 20 feet, and then he'd pull up about 2 feet and then set it back down. He'd lost. Pull up another 2 feet, he'd lose it. Another 2 feet, he lost it. And so, I mean, as soon as we pulled out, formation just collapsed in on us. And the only way we got through was that we re-drilled it with a rotary bit, and then as we backed out, we dumped cement down through the bit to cement the formation as we were coming out. And that was the only way we could stabilize it. It was a nightmare.
Also, did you have to measure the redox potential of the water?
No. I think probably we'll be able to do that when we do the pump test. When we were doing this sampling, we had to airlift. That was the only way we could try to purge the drilling fluids out of the hole, and be pointless. Yeah. Okay.
Did you just flow down the hole?
No, we didn't have flow to the surface. We had to lift the fluid from 1,800 feet back to the surface. And we did that as one of the driller's tricks is you go in with the drill string and pump high pressure air down and displace the water above the end of the drill string, and it lift it to the surface. And it's a crude way of pumping fluid out of the hole, but it does purge it sufficiently where you can get at least a water sample, and one that is not totally contaminated with drilling fluids. Steve, yes.
Hey, Don. Old people talk about old days. I always remember the geothermal well that you and I
Yes.
took part in. We were trying to get some water samples, right?
Yes.
From the whole go right back. And what you've done always exciting. And always turn up something new.
Well, I
take my hat for what you have done, because without you being around, why I don't know who that the army would turn to look for water. I remember many years ago, John Link and I went over the Saddle area many times. He said, "Oh yes, they're looking for water, all right, and but you are able to get money from it." That's the difference.
Oh.
And now we all stand to benefit.
Yeah.
The science stands to benefit.
Yeah, I hope so.
Having said all this, right, and I have you, in your team, it's a team effort, right? You have climatologists in your team. When you talk about, maybe quickly, why did they bring in the climate? It's kind of obvious because that it's hydrology and water resources tied together. And so we're, my simplistic way of looking at hydrology is dictated by climate and geology. Okay. You addressed it somewhat, a little bit. the way the climate as of now. But this mountain has grown, very growing up, it was very low altitude, and the climate was entirely different than it is now. The recharge could be, from rain, could be quite abundant when the volcano is growing. And you already mentioned that this water is very old, right? Oldest that you've seen.
Yes.
So really, we're probably seeing some of the very old water when the volcano was low, and being recharged by the trade wind and what have you. But now it grew to, where it is, well, then the climate zone is completely different. As a matter of fact, the volcano passed through several climate zones now. And so, let me make the point about water resources. The Army was sustainable water sources. And so I think in your concept developing a conceptual model, you really have to get the climate evolution involved together with the geology.
Yeah.
So that they say, oh, yeah, we're mining some more water, which is not necessarily sustainable.
Right. Well, this certainly could be, and this has certainly crossed my mind, that this water is almost old enough to go back to when Mauna Kea was last glaciated. And the way that right now I'm thinking about this is that, okay, if these, we're dealing with dike impounded systems, the top of the water table in this particular compartment is about 1,100 feet above where I was able to sample the water. Now, when we go in and do our pump test, what we're going to do is perforate the well closer to the top of the water table. And if I can manage it and manage the cost, I would like to actually perforate down through the water column and then look at sort of the stratified chemistry and age as we go down into that water table. Because it wouldn't surprise me for this water at this depth, 1,000 feet below the top of the compartment, to be relatively stagnant. You could imagine a situation where it doesn't overturn very rapidly. I think what will be sort of more interesting is what we see at the top of that compartment. If that water has a much shorter residence time, then that's going to tell us that, okay, within the sort of the upper parts of this impounded system, there is relatively rapid recharge and turnover of that water. If it turns out that that water, though, is also approaching 10,000 years of age, then that's a very different story. And one of the things that we've discussed with the Army is that, okay, if they develop a production well, that we use this borehole as a monitoring well. So this will then allow them to monitor the impacts of their withdrawal. It turns out their water demand is actually pretty minor. It's a relatively low use rate within the camp. So it's possible that their demand is not going to significantly impact this water supply, but in any event, what our hope is that we'll be able to use this well as a monitoring well and track the impacts of whatever utilization they do have. As well as, I think, you mentioned climate. This will give us an opportunity with this well, maintain it over the long term, and see how the effects of climate change impact this groundwater system. Something that possibly few of you are aware of. Up until about 2 years ago, there were springs high on the slopes of Mauna Kea. And the Army derived a lot of their non-potable water for operations there at PTA from those springs. Those springs are almost gone now. And likewise, Lake Waiau is almost completely dried up. So, we are seeing the effects of climate change on Mauna Kea very clearly. Yes?
I suggest you get a Japanese water bottling company. It might pay a lot of money for 10,000-year-old water.
They might. They very well might. I don't know. Although our 2,000-year-old water, I probably talked to a dozen potential water bottlers, and none of them actually came through with. Okay. Yes, sir.
In your opinion, is there any reason to suppose that what you discovered on the Big Island might not hold true for the other Hawaiian Islands?
Certainly, it's possible. But looking at sort of the interpretation that Ashton came up with these large dike systems, to me says, hey, let's go look. And that's really sort of my long-range plan, is to go and see sort of what the relationship is between these inferred dike systems and the groundwater systems on all of the islands. So I think, again, we've had this picture in our mind of sort of the classic, basal groundwater system, and sort of assumed that we were limited by the elevation of the water table here, that there were no boundaries out here in the body of the island away from the central calderas and rift zones. And Garrett's data says otherwise. Yes?
One complication to that model is Mauna Loa is relatively unique among the islands in having these radial dikes. And some of those radial dikes, well, all of them, many of them point towards the northwest, to this area you're finding water. That may not be the case. Well, it isn't the case on the other islands. You don't have those radial dikes.
Well, you don't see them at the surface, but again, that gravity data shows significant dike complexes sort of surrounding the central conduit. They may not make it to the surface. And again, I take the interpretation of from that paper at face value. I'm not saying that it's gospel, but it's a good starting point. And that's why we're going to be going out and collecting some more gravity data and trying to help refine those models. I'm not saying it's there. I'm just saying it might be there.
But I guess, don't we have enough wells on Oahu, for example, that could have shown some excess in the future?
Well, I'd have to go back and look at the gravity model for Oahu. I think most of the dike system is confined to the sort of the area immediately around the Waianae caldera and the Ko'olau caldera. I'm not saying it's everywhere. I'm just saying let's go take a look at that model and see where these dike complexes may exist, and see if we can find a correlation with the groundwater.
By the way, how much time does a survey, the geophysical survey, take? Is it expensive?
The geophysical surveys themselves don't take much time. It's the analysis of the data that takes time, I'm afraid. But we're hoping to finish actually the surveys either by the end of the year or early next in January in the PTA region. But it probably will be 6 months or so before we have really processed the data and have any sense of what sort of that three-dimensional picture may look like.
And if it is possible, would different snapshots at different times show some dynamics of water?
Certainly, if you can image the water table, and one of the advantages of the MT technique is that you can image conductive or non-conductive or less conductive zones, and then underlying less conductive zones. You can actually see a significant depth into a conductive region. Whereas with the audio magnetotelluric, as soon as you hit a conductive region, as soon as you hit a saltwater horizon, you're blind below that. And so, we're going to try to extract as much information from the MT as we can. But there's a lot of work to do. I'd like to apply for my job all over again. I don't know if I'd get hired, but...
Tell us a little bit more about your proposed pumping test. It sounds like you're going to perforate the casing and various stones. Are you going to pack them off?
Right. Well, what we have to do, again, at 4-inch diameter inside of our casing, we're not going to put an electric pump down there. What we have to do is, there's a specialized type of pump. It's called a moino pump. It's a positive cavity displacement pump. It's like almost, in a sense, like a piston pump. What we'll do is put the pump body, we mount that on the end of the drill string, and we actually have a packer below that, run the pump body down to where we're going to pump from, and then we actually lower the impeller on a drive shaft and lower that into the pump and then drive it off of the drill rig. So the rotating head on the drill rig is what's going to lift the water up to the surface. And what we can do is go in, we do the perforations, go and set the packer down below the perforations, pump on it. We'll have instrumentation essentially below the pump to sense the hydrostatic head and look at the drawdown while we pump. But we're limited to something on the order of only 40 GPM. These pumps, again, we're going to have to generate 800, 900 PSI to lift that water to the surface. And so they're high pressure but low volume pumping rates. Yeah. Okay. Other questions? Okay, thank you.